Every time I build myself a microprocessor based project like this one, I always worry about making it work. It sounds silly, I know, but unlike making a radio or an amplifier, you can usually trace it from one end to the other of the circuit and see if you can work out where the problem is. But unfortunately with this, the problem could be absolutely anywhere. If the thing does not work, or even worse, it works intermittently, the problem could be absolutely anywhere on that board. It could be your wiring, it could be a component wrong, you could have all sorts of things wrong with it. So the very first thing you want to do when you are designing a project like this is think about it before you start. Think about it in respect to where you're going to put the components. Will they all fit on the front? I wasn't sure I could fit these all on the front, so therefore that's why I decided to put these on the back. As it so happens, I possibly could have put at least one of them down there, but it really would have made it a bit tight, I'm sure you agree, just in that little bit of space which we have left there. The thing which you must use with ICs will be sockets. All too easy to think it's not worth having these, or, well, you know, it's too expensive. Sockets are not expensive compared to the harassment of finding that you need to change a chip just in case it's that's faulty. Certainly I would never suggest you do anything other than use a socket. The two main types, I mean there are obviously other sorts as well, which you'll find these days, is the turn pin ones, and this one's are just ordinary folded contacts, tin contacts. What I like about these is the fact that they have nice sharp pins. They're very sharp, and when you're using the wiring pen, it catches on them and it makes it easy to actually run your wire between the different legs. Unlike these, which are turn pin, you can see they're round and they won't, and the wiring pen slips around and you have to stop it with a scalpel sometimes and then pull it tight. But the advantages of this is it doesn't wear out in the same way as this does, because the contacts tend to pull out with the ICs if you keep taking an EEPROM in and out, for example. But this is much more difficult to locate in the first place, so you can see there's advantages and disadvantages of each. But what I've done, as I'm sure I've shown you before, is this one I've actually used where I'm using an EEPROM. I stacked them one above the other, so if I damage the pins, I simply take out the top one and plug it into the bottom one. This is the next thing we mustn't forget about, and they are called decoupling capacitors. It's always an idea to use one of these per IC package on your board. Usual value is 0.1 microfarads. You can usually fit them in somewhere between the ICs and in between the sockets. However, if you feel like it, I buy these things. These are surface mount components. If you feel your solder's good enough, these will actually fit very nicely between tracks on VariBoard, which means they take up almost no room whatsoever. But you have to be have a pretty good soldering iron for that, and hold them down with a scalpel, say, while you solder them. But that's just a thought. But otherwise, just simply use these small ones. For my wiring, I use these wiring combs, and these fit, the little pins fit in the sockets in the VariBoard, so not sockets, the holes in the VariBoard, and they're the right pitch, and then your wire goes between them, backwards and forwards between them. You obviously have to decide how many you want, up, down, sideways, whatever. You can see we've obviously used these here. Some of them go across the top, others go down the sides, you can see. So you have to sit down and design, and this comes into the initial design. You must put that into your design, work out where you're going to put it, and obviously don't forget your mounting holes, because you may want mounting holes if you're presumably going to mount the thing. So you know, these are the things to look out for. It's worth bearing that in mind. Certainly that's the thing to start off with. You start off by working out where your sockets are, putting these into position, and then consider your wiring. So for wiring, if you're going to go about it this way, I've used much thicker wire on occasions on some of my earlier projects, but I tend to use this stuff, which is on a wiring pen, and it's a reliable, easy way to do it. The wire sits in the little reel at the end and comes out the other end here, and you wire between one pin and another pin through the combs. That's the whole idea how it works. This wire it does have a rather nasty coating if you burn it, so when you heat it up with the soldering iron, watch out you have adequate ventilation, because I have some funny feeling it's some sort of cyanide thing that comes diisocyanate. I can't remember what it's called. Toluene diisocyanate, I think that's what it's called. So yeah, I might be right, I might be wrong. But you don't really want to breathe that stuff in, so that's worth bearing in mind. But these things are incredibly useful. Likewise, you can of course buy different reels of different gauge wires and also thicker ones for power if you choose to use them. I generally go for a separate piece of wire to do my power, but some people like to use these. Next thing to remember is working out your power rails, whereabouts the power rails go on these. I made a mistake when I did the 68,000 because, hence the fact you notice that there are lots of little wires running up and down the sides. I made a mistake because usually with most TTL the bottom right hand corner is the minus and the top left hand corner is the plus. It doesn't always apply. There's some ICs like the 7490 where they're 3 in from the end on both ends. That size of course. But on this occasion I made a mistake. I was looking at the back of it and thought, oh, I know, I put the minus on this side, and of course that's why we have a black socket down here. And my big mistake, which meant that all of my wiring had to be taken right the way up to the other end. You can see the wires, whereas with the Z80 base one there are no such wires on it because I didn't make that mistake. Anyway, that's as far as that goes. But so you need to check that. Then back on the power side of things, you need to check for the other pins on the circuit that need pulling up. Pulling up, by that you don't, in good practice, don't leave TTL legs floating around. You certainly don't leave CMOS legs floating around. You tie them either high or low, preferably through a current limiting resistor, just to give them a logic high. So that's certainly worth bearing in mind. The next thing to consider before actually starting making it is what board are you going to use. And we have two different sorts of Vario board here. One is with the little pads. They're 3 pads, and that's the one I use for the 68,000, whereas I use the continuous strips for the Z80. They're both exactly the same pitch, but you have no full length tracks. If you use these, that's why you have to put wire on anyway to link the top to bottom to give you your plus volts. But you need to cut these. Not so much so with these. It's still necessary to cut a few of them when you have these pads, but certainly with the long ones you should use a Vario cutter, and that's what this fella is. Some people use a drill. Why not just buy a cutter and be done with it? It's so much easier using that, and that you use to cut the tracks where needed. Here you can see, for example, the track cuts where the screw will go, and you don't want the screw to short out any of the tracks. Likewise over here you can see there's more, and across here. These are all ones which are done with the Vario cutter. So you can use a drill, but honestly for the cost of one of these and convenience, it's much better to stick with that. Obviously there are other track cuts you'll do with the little pads where the three hole pads are connected together, like on the 68,000. But so still same things apply. It's a good idea to use one of those. Invest in one. On the subject of tracks, do check the full lengths of the tracks before you start construction. I recently bought several of these boards, and for all I know this is one of the ones, and I found there were a couple of bits where the tracks had not been etched, and there were tiny whiskers between the adjacent tracks. Now the way to spot that obviously is use an eyeglass. Another worthwhile investment. And I must admit, I don't know how difficult it would have been for me to find it. It may well have been easy. It could well have caused no end of problems when you could hardly see it. It was hardly visible with the naked eye, where some of the tracks had not been etched across. There were a couple. So it's one of these boards. I don't know, it could have been this one for all I know. And if I hadn't checked with that eyeglass before I started, then I would have had a problem. When you're finally ready to start building, great. Put in your sockets first. Do your power rails, etc, etc, and then keep double checking stuff. Take your meter out and make sure that you have connections between your power rails and the appropriate plus and minus connections to your ICs. It's all too easy to make mistakes, and the problem is the worst thing is correcting mistakes with circuitry like this where there are so many wires is extremely tedious, and you may well create other problems in the process of doing it. So don't forget to use your net list. The net list obviously holds what you need from the most repetitive bits, each one where it's joined to a bus is connected to several devices at once. It's best, I like to have those out the way because the address and data bus is always a bit of a chore, so I like to have them done first. While we're talking about the initial design, I always like to put a socket in for one of these. It's something you don't want in every project, but for the cost of a small socket, it's well worth having that there, because once you're debugging it, you're checking the thing works. If you can actually have a display which you can see something on, like we saw with the 68K, that you can always take it out. You can take that out afterwards and you don't have to use it. The socket is there. So I'd strongly recommend anybody build one in there. Very, very easy to interface. There's a couple of address buses, the data buses, and a write line, and that's it. So it just takes up an I/O, and if you think you're going to use that I/O output for something else, then fine, connect it to your other thing, but also connect display. So once you take the display out, then you can use it for what you wanted to do. So that's what I do. Likewise, the LED. Having once plugged in one of these processor boards back to front on the power supply, and it took me a while to sort it out, I did lose a couple of ICs over it. Why? Because it wasn't perfectly clear. If I'd had a LED to show that the power was on, then it may not have, I may have been able to spot it quicker. So I'm just saying, from my own experience, I made a mistake. I don't want to make the same mistake again. Hence, all my projects, I like to have an LED on it just to show that the power is up and is running. So when things are moving and you've already started doing some wiring, as soon as you've done the reset side, then I always like to suggest checking that out first. There's the reset capacitor, for it resets when it switches on, resistor, and the other bits and pieces, the IC, are on the other side. So I think that's a worthwhile comment to make. Once you know everything's working, on that side of it, check it out and make sure the reset is okay. The next thing to talk about is actually very similar. It's the crystal oscillator, which we have here, and that can cause problems. We have this connected up with three gates from this LS14 to give us our 4 MHz oscillator. There's Schmidt trigger inverters in there. What problems can you have? Well, it may not oscillate at all, but on occasions, if a component value isn't quite up to the standard this thing wants, or if it's slightly out of spec, or for whatever reason, you'll sometimes find that can oscillate at the wrong frequency. So if, for example, this is a 4 and it's running at 8 meg, the odds are that your circuit's not going to work. Or it might just try to work and then fail. So once again, you have another problem you have to solve. This is certainly something I would like to check each time I make something. I personally do not have a nice expensive frequency counter. I've often meant to build myself a good one with a good resolution, but at the end of the day, I just bought a cheap and cheerful Chinese one with a pick. It's a couple of pounds on Fleabay, and I've interfaced that with a little board of my own, which gives me a nice analog input as well as obviously a digital for that, and that works fine. That's all you need. Invest a fiver in something like this, and that can check your frequency. Or of course, if you have an oscilloscope, you can check it on the oscilloscope. As soon as you start loading ICs onto your board, into your sockets, then the thing to do is be very careful. Why careful? Well, this IC looks fine. Put it in the board, it'd be fine. But if you catch one of the legs, you end up with a situation like that. And with the folded up leg, you can end up with no end of problems. And it's not always easy to identify it, because of course if it's pushed down it might make contact. Then you twist the board a little bit and it doesn't make contact. So do be careful how you put them in, and always double check that no legs are caught underneath. When you come to put the power on the board for the first time, another recommendation is to connect a meter on amps and see how much current it takes. It's always an idea to gauge just how much it might take. Straight away this is going to point to some problems. If, for example, with this particular board, if we found we had, say, argument's sake, 50 milliamps from it, you'd know it's wrong, because the 68,000 takes a lot more than that. So in fact, in reality, we have two figures here, with and without display, because remember the display will add some. Without the display, this takes about 312 milliamps, so that's the processor, and these are all TTL. That's TTL, these are TTL LS. These don't take very much, the ROMs and the RAMs. That's another LS, and this, the 2LS on the back. So that sounds about right. And then it's 340 when we have the 68K message up here. So it goes up from 312 to 340 as soon as you enable that display and you have the LEDs glowing. So it's always an idea, it's a good idea to preempt what might be at fault before you actually come across it. Obviously if it goes really high, turn it off. There's a short, sounds to me. If we assume for 1 minute that you've built this and you put a simple program in the proms and you put them in there, you turn it on, how do you check it's working? Well, assuming there's no routines that will drive the display or anything, if you remember we showed you how to do that. What you do is you put a simple loop in the case of this particular unit, and these proms here, we did the loop at 400, that's 0400 hex, and that would be something we can actually go on to check that it's going to the right place. Just out of interest, the good thing about this compared to the Z80, or many things I know, is that the Z80 has dynamic RAM refreshing circuitry, which means you cannot do this with the Z80, because the Z80 will disappear off and do its RAM refreshing in the middle of your simple circuit, so you can't do what we're going to do now. So what we did, if you remember, let's have a look at the sheet. If you recall back to the last video, we tested the pins on the 68000 and we found, using the address pins, we went up to A11, I seem to remember, and on A0 there was a toggling, and that was an oscillator, toggling pin. These were all low until we reached A10 and there was a high on A10. So that's exactly as we found it. We could do it now, but there's no point in doing it. Have a look at the last video if you actually want to see me going along with the logic probe and the scope, and you can actually see we're checking these out. You find that everything is low except for these two pins, one of which is toggling, that's going up and down, and the other one is steady. So if we now relate that, this shows how you can do this anywhere you like in the program when you're actually debugging. If you want to debug a program and you're not sure where it is, put a loop in and see if it loops, then check where it's looping. We can do that with the 68000 because it doesn't have the dynamic memory refresh. And if you look, if we now break that down into the hex values here, you'll find that A10 is actually a 4. That's obviously 0, that's a 0. And this toggles between 1 and 0. And of course that ties in with the program that's looping at 4000 or 4001. So using this whole principle, you can put in a loop anywhere you like in the middle of your program. If you tell it to go jump somewhere and you're not sure whether your program actually jumps there, then you can put the loop in and you can check it out. Put the loop in temporarily, run the program and see if it's looping. That's what I tend to do. Obviously, if you're using an assembler or if you're using a 68K fake program on a PC where you have an emulator on it, then you'll be able to do that without doing this. But certainly for somebody who's doing it at grassroots level like myself, this is the only way you actually have a connection with the programming side. If, however, the thing does not work, even with your simple program in it, there are a number of steps you can take. I would double check my wiring and make sure that all the wiring is correct according to the netlist and your circuit diagrams. Double check it and triple check it if necessary. Sometimes when checking on the back, one forgets to reverse, which is 1 and which is 14, for example, this sort of thing. But do it and check it carefully. Likewise, then check your these are all static checks, by the way. Use them with a meter and check that everything appears to be where it is. The next thing to do is, with the thing running, try a dynamic test and see if you can actually spot one of the levels is being held down or it's being held up. Look for something that should be toggling and it's not. It's only going halfway. Something is obviously holding it down. I did find a fault on this thing. I did have this IC. I bent the legs around. This little fella, this 14, was actually faulty. And I haven't had a faulty IC for absolutely years. This one's from 1986, but that's no excuse for going wrong, is it? And this one had one of the gates at the end was it didn't do anything. It was simply high, and it was holding up another gate somewhere else. So it's quite easy to find that particular fault. That was quite easy to find. Whereas others I've known are not easy, particularly if they're internal to the chip and there's nothing on the outside to prove there's something wrong with it. Well, that's about it for this short video. I hope that somebody will have a try at making one of these, and if they do, they have all the success. If you have any comments, do please put them in the comments below. I always like to see the comments. Otherwise, you can always tell me if you made one and it works. That would be even better, wouldn't it? Anyway, thanks for watching.